So here's the deal. For those of you who don't remember or like to just kind of have a reminder, what we were doing last week involved using your very own personal air carts to explore the behavior of objects in collisions. So this is a great example of a collision, and I think I can change the speed of this. I can change this to half speed so that we can watch this collision unfold a little bit more slowly, and boom, off they go. And what I told you a while ago was that there's this quantity called momentum. And momentum, we can find it, we can compute it pretty easily by multiplying two numbers, velocity and mass. Multiply velocity by mass, you get momentum. And then we talked all about so under certain circumstances, one of the things that's really neat about momentum is that it's conserved, which means if we know how much there is at one point, we will know how much there is at some later point. And I even gave you an example, like a real person that I met who was a physicist who did this work for insurance companies where he got paid boku bucks to analyze collisions just like this one right here. And basically what he would do is he would look at things like, okay, well, if I look at where these carts are after they've hit each other, if I know just a little bit of information, I can go back and figure out how fast they were going, and I could even potentially figure out if there was an accident, who was at fault. And that is a pretty powerful, that's a pretty important thing to be able to do. It's really useful. So what we decided is that much of the time, this momentum thing is conserved. It stays the same, at least if we look at it like right before and right after things bonk into each other. And we did a bunch of work. We were kind of playing around with that, practicing, trying to figure out under what conditions and what kinds of predictions could we make. And you all did a whole bunch of work with that. And now you're working with your very own air carts. And what I told you to do was make some measurements, make some computations, and then evaluate whether or not momentum was conserved. Yeah?
Our projects from our last class, our things, are we going to get a work on?
Let's defer that till later. I'll answer that, but not right now. So here's the kind of stuff that's, to me, that's pretty neat about what we're doing, all right? So the first thing is, in this particular collision, it seems like maybe momentum should be conserved. So we can start with this idea that this quantity, and how I described it to you is, it's how hard something is to stop. So that stoppableness of these objects sort of stays, there's something about it that stays the same, even after they've bonked into each other, and even when they're moving in different directions and stuff like that. So what I want to do is just really quickly show you how I can calculate the momentum of each of these carts before and after the collision, and then how we can evaluate our work and use that to evaluate this collision. So the first thing that I need to do is I need to figure out how fast each of these carts is going before the collision. So I'm gonna do these measurements really quickly. I'm gonna do 5 clicks. This cart on the left, after 5 clicks, 1, 2, 3, 4, 5, looks like it moved about 20 centimeters. So I'm just gonna write that down. It went 20 centimeters in 5 clicks. And now I'm gonna look at the cart on the left. That can work. Okay, so let's see, I'm gonna start here. It starts at about 90. 1, 2, 3, 4, 5, and it went to about 77, so that's about 13, and about 13 centimeters in 5 clicks. And now I'm gonna, so you don't need to write this down. I'm gonna have you write some stuff down in just a second, but you don't need to write this. And now I'm gonna look at how they move after the collision. So I'm gonna look at this cart again on the left, and let's see, at this point, it's at about, that looks like it's at about 63. 1, 2, 3, 4, 5 gets it to about 54. 4, so that's 9 centimeters. I'm at 9 centimeters in 5 clicks. And the other cart, let's see, we'll start it there. That's at about 76 or so. 1, 2, 3, 4, 5. Gosh, it only went like 1, 2, went maybe 2 or 3 centimeters. That's not that many. Let's say 3 centimeters in 5 clicks, okay? So, so there's my initial data, and then this is the part that I do want you to write down. So you don't need to write down these tables, but I want you to write down the numbers that I get so that you can see. So we talked about how we can find velocity by multiplying the number of centimeters by 30 and then dividing by the number of clicks, and that'll give my velocity in centimeters per second. So let's go ahead and do that. So for my cart on the left, it's 20 centimeters times 30 divided by 5, and that ends up being about 120. So I'm gonna put 120 in here. So my initial velocity is 120. And for that same cart after the collision, it was 9 centimeters, so 9 times 30 is 270 divided by 5 clicks, 54. So its final velocity was 54. And Sam and Trey, this was yours, right? Well, so this cart on the left, whose was it?
That's me.
And how, do you remember the mass?
Pretty sure it was 151.12.
151, about?
Yep.
Okay, and Sam, how much was yours?
206.
206, okay. So we can put those numbers in as well. So our mass was about 151 for Sam's cart. Okay. And now I'm gonna do the same, or sorry, for Trey's cart. For Sam's cart, the mass was 206. And the initial velocity would have been, it went 13 centimeters times 30 divided by 5, so that's 78 centimeters per second. And the final velocity was going pretty slow, 3 centimeters times 30 divided by 5 gets me 18. Okay? So these are my masses and velocities for this collision for both carts. And then I can find the momentum for each of my carts too. Momentum is just mass times velocity. So I know the mass is 151. 151 times 120. Trey's cart had an initial momentum of about 18,120. And it had a final velocity, 151 times 54, of about 8,154.
Is this what we need to be writing down?
Yeah, go ahead and write down these numbers so that you can kind of keep track of it on your own. Yeah.
How did you get 54? Because 13 times 30 divided by 5 is 78.
Oh, did I write it down wrong?
I think you
I might have used the wrong one. Yeah. Yeah, I might have. I did. So this was, I don't know, which one did I write down? Did I write it down right over
I
here?
think the top is Trey's.
Yeah.
Wait, then why did you?
No, it's
This
left
was,
to right.
this is Trey's cart,
Yeah.
and this is Sam's cart. Before and after.
Oh, okay.
Yeah, I think I did it right. Did I do it right?
Okay, wait.
Yeah, I think I got that right. Yeah. So it should be, it should be 9 times 30 divided by 5 is 54. Yeah, so that's after the collision, Trey's cart after the collision. Yeah. Okay. And now let's look at the momentum for Sam's cart. So his cart had a little bit more mass, 206 times 78 should have been about 16,068 before the collision, and after the collision it should have been 206 times 18, which is about 3,708. And then what I said was, if we add the total momentum before the collision, this plus this, we add the total momentum after the collision, this plus this, then we can find like overall how much momentum there was. So before the collision, it looks like 18,120 plus 16,6068. I get 34,188. And for those of you who like to think about units, this would be grams centimeters per second, but you don't have to write that down, that's just ridiculous. And then after the collision, it's 8154 plus 3708. And I get 11,862. So I just did a bunch of math, and I came up with a bunch of numbers. Here's where it gets interesting. I told you that momentum, in this case, should probably be conserved, or pretty close to conserved, which means that if we know all the momentum at one time, which we did, it was this plus this, that should also tell us the amount of momentum later on, which is this plus this. And I didn't do a terrible job of collecting data. I might have made some mistakes. I don't think I made any dramatic mistakes. But look at how much different my momentum is. The beauty of being thoughtful about doing work like this is when I look at this, I know I did something wrong. I think Jay saw it, and I think Oscar saw it too.
You missed a decimal point, I think.
I might have missed a decimal point. I'm not sure that's what it was though. It's possible that I missed a decimal point.
34,000 as your initial momentum is a little bit high because normally you get around 2,000 to 3,000.
Did you?
Yeah.
I'm not sure about that. I think if we multiply 100 by 100, you're going to get on the order of 10,000.
Oh, yeah.
I don't think I missed a decimal point.
Where did you multiply 100? Where's 100?
On the order of 100 times on the order of 100.
Oh.
This is somewhere around 100 times somewhere around 100. This is going to be somewhere around 10,000. So, but Jay saw what I did. Does anybody else see the mistake that I made? I made a pretty easy mistake. I made a mistake that is super easy to make. I bet you a whole bunch of you did it as well. That's why I'm showing you this right now. Liam? There's no negatives. Is that what you were going to say, Phoenix?
Yeah, there's
Is that what you
negatives.
saw too? Yeah, so here's what's crazy about this. Direction matters. Before the collision, these carts weren't moving in the same direction. Yeah.
Wouldn't the final velocity be a negative since it's going backwards?
Yeah. So here's what we have to do. We have to make some adjustments. And luckily, most of them are going to be pretty easy. Before the collision, Sam's cart was moving to the left. It had a negative velocity. After the collision, Trey's cart was moving to the left. It had a negative velocity. That means that this velocity here should have actually been negative, and this velocity here should have been negative.
That's car mass. Cart mass.
Oh, yeah, thank you, sorry. Hang on. Yeah, this should be negative, and this should be negative. That means that after the collision, Trey's cart had negative momentum. What is negative momentum? It's nothing special. It's just momentum this way. You can have momentum this way, or you can have it this way. If I try to slow something down and stop it if it's moving this way, I'm not going to get much mileage if I push it this way. When you push something in the same direction it's going, it doesn't slow down. Negative momentum just means if it's negative, you have to push it this way. If something has positive momentum, you have to push it this way to get it to slow down. Yeah.
I think your initial elastic is incorrect because I got 151 times 120 is 18,120.
That's what I have.
Oh, okay.
Yeah.
Wait. What's the bottom then?
This is the total momentum
Oh,
of both of
cars.
those cars combined, yeah. And that isn't right, by the way. So if Sam's car had a negative initial velocity, then it has negative initial momentum. So if I do these calculations again, but I include the negative signs, I'm going to get something different. And I'm going to get something that actually looks much more like what we would have expected. if I add 18,120 and negative 16,068, I get a total initial momentum of 2,052. Yeah.
If you have the bigger number with, when you have the bigger number in the front of a negative, you can just subtract the negative number from the positive number. But if the negative is in front, then you have to do the negatives.
Yes, yeah, and so you can add with a negative sign
Yeah.
too, either way, but yeah. So when I add these two together, I'm gonna end up with a negative number, negative 4,446. So those are not identical. We're off by about 6,000 here, but before we were off by about 20,000. So this is way closer. And we talked about this collision the other day. Remember I said something went a little bit awry here. What happened, and we'll watch it again. Yeah, it bounced. It did the bounce. So let's go back and watch it again in slow motion and see right there. That's where Sam's cart lifted up. We lost momentum there. What kind of momentum did we lose? Well, his cart would have gone this way. That would have been positive momentum. We lost some positive momentum in this collision. And it is exactly what we would expect to see. Momentum was sort of conserved, but not completely. It lost some. If it had actually been moving a little bit faster here, we would have had more positive momentum this way. So it's hard to know exactly how fast it would have gone, but we could figure it out. I'm not going to right now, we could figure it out. What I want you to see is when you look at your work critically and you think about like what you should see versus what you do see, then it actually kind of can sometimes jump out at you that you made a mistake. Now, if I were doing this for real, if I were you and I were doing this for real, if I got to this point and I looked at these two numbers, these still look pretty far apart. But when I look at the video, I have an explanation why. This seems reasonable given the video that we just saw. It might be that that's not quite right. People have been flagging things that might be mistakes all period long, and that's really good. You should do that. I want you to do that. Oscar saw a couple of things. He was like, wait a second. And I don't remember who told me just now that I was putting negative signs in front of the masses, but that wasn't right. Yeah, Phoenix got that one. So yeah, I make all sorts of mistakes, and especially when I move in quickly. I think this seems reasonable to me. If it really mattered, if I was going to get paid for doing this work, if I was a forensic physicist and this actually mattered, then I would do it again, and I would do it again and again and again and again, just to make sure. I would have somebody else verify my numbers. Sam and Trey, is this close to what you got? Yeah, so we did verify this. Yeah, so pretty close. Not exactly, because we probably counted different spots or whatever, but so here's what I would like. I would like you to take about 10 or 15 minutes, and I want you to go through your own work and your partner's work, and if you can step in and help some other people, I'd like you to go look at their work as well. If you didn't get this done, then you can have this 10 or 15 minutes to continue working. If you got it all done, then I'd like you to use this 10 or 15 minutes to really carefully check your work. Most of the time in this class, I give you points based on what I see you doing and the effort that I see you making. And that's really not going to be any different today. It's just that today, since I'm giving you time to find mistakes and potentially correct them, I'm going to be looking with a little bit more of a critical eye. If I see obvious mistakes, like negative signs that aren't right, I will kind of count that against you, because I want you to take this time right now to get all that stuff addressed. Yeah?
Do we need to turn in our notes?
You don't need to turn in your notes for today, but I do want you to, as you correct your work, I do want you to resubmit. If you turned something in on Friday for the air cart data analysis assignment, I want you to resubmit it so that it's correct. And then the last thing, I just want to remind you that you have a job, and your job is every day, same thing every day. Be here when you can, use your class time productively, and then turn in evidence of your learning. with Ms. Reinwald not here, if there are people who are having trouble staying on task, if you're not doing your job, I'm just gonna ask you to go up to the behavior room. So just be aware of that. If you, for whatever reason, are having trouble focusing, today's not gonna be a day where we'll try to accommodate you. Instead, just have you go to the behavior room, and you can, if there's work you can do up there, that'd be great. If you just are having an off day, you better believe I get that 100%. So if you're having an off day, that's okay. It's just we'll have you have that off day up in the behavior room. Okay, I'm gonna shut off the video. If anybody has any questions, let me know. We are gonna do this for about 10 or 15 minutes, and then we're gonna move on to bigger and better and more awesome things.